Hello friends, welcome back to the channel, and in this video we're going to take a look at the recursion strategy for algorithm design. Recursion is a technique we use when a function or module delegates work to clones of itself. Such a function is called a recursive function as it solves a problem defined in terms of itself. Many programming languages implement recursion by means of stacks. Generally, whenever a function calls another function or itself, the caller function transfers execution control to the callee, which may involve some data to be passed from the caller to the callee. This implies that the caller function has to suspend its execution temporarily and resume later when the execution control returns from the callee. Let's take a look at the famous Fibonacci sequence problem, which we can solve using the recursion strategy. The Fibonacci sequence is a series of numbers in which each number is the sum of the two preceding numbers. It starts with two ones, and each subsequent number is the sum of the two previous numbers, and this will give us a sequence of numbers that will look something like this. So the question is, how can we call the function that will return the nth Fibonacci number, and how can we utilize the recursion strategy to solve this problem? Well, let's first describe this problem using pseudocode. Let's start by defining our Fibonacci function that will take one argument, which will be the nth Fibonacci target. Then, inside that function, we add an if statement that will check if the target value is less than or equal to 2. If that check is successful, our Fibonacci function will simply return 1. But if that check fails, we then have to return a result that we get from adding the results of these two recursively called Fibonacci functions. Here we have two recursive calls. The first one is subtracting 1 from our target value, and the second one is subtracting 2 from our target value, and those values will then be passed as arguments. Each stack that makes recursive calls will have to wait for both of its recursive function to complete first and transfer back execution control. Let's say we want to calculate the 6th Fibonacci number. First, our target is 6, so our if statement will fail since 6 is greater than 2 and also not equal to 2. Which means that we have to recursively call the Fibonacci function again, but this time subtracting 1 and 2 respectively from our target value. By doing that, we now have two branches or stacks, if you will. In the first one, our target is 5, and the second one, our target is 4. For each of those recursive calls, you can see that the if statement checks will fail again, since the values are both greater and not equal to 2, which will result in two more branches or stacks from the current ones. We continue to repeat the process, and eventually we'll get to recursive calls where the target value will be less than or equal to 2, which means those recursive functions or calls will then return 1 to their respective callers. Now we can see that these stacks will return 1 for both fib2 and fib1, which will result in 2 after adding them together for fib3 here. All the other stacks here will return 1 as the result value since their fib targets were less than or equal to 2. With this, it means that on fib4, the result is 3 since we added 2 and 1 from the recursive calls here. For fib3 here, the result will be 2, and the same applies for fib3 here as both of their recursive calls returned 1. Lastly, fib2 here will have the result value 1, then we move up again, returning the results and adding them together. Here on fib5, the result will be 5, and for fib4 here, the result will be 3. Then we finally return both of those results to the first stack, and the result we get from that will be 8. So it will mean that our 6th Fibonacci number is 8. Let's see how we can implement this Fibonacci function. Alright, so implementing a function that will generate the nth Fibonacci number using the recursion strategy is pretty straightforward, and we can start by defining our function here that we can name Fibonacci, and this will take one argument of type number as well. So we can name that argument target, and with this we can implement the rest of the logic for our function. We're going to start by checking if our target value is less than or equal to 2. If that's the case, we simply want our function to return 1. But if that's not the case, we want to return a value that we'll get from, firstly, recursively calling Fibonacci, but this time we're going to be subtracting 1 from our target, and that will be passed as the argument. And the value that we get from that, we want to add it to another recursive call that will make to the same function, Fibonacci, but this time around we want to subtract 2 from our target. And with that, our Fibonacci function is complete. Now we can test it out. So let's create a variable here that we can name result. think that's a fitting name. And we can call Fibonacci, and this time let's say we want to check for the 6th Fibonacci number. So let us terminate that, and I have a typo here that I need to fix. And with this we can log out the result and see what we get. So let us do that here on line 11. So just save the file, open the terminal, and we can run our JavaScript file in this case, and I named it Fibonacci and .js. Run this and we get 8. So we can also change the Fibonacci number here that we want to get, let's say to 20. Save our script again and then run it again, and we get the result here. So the time complexity of the recursion strategy depends on 2 factors. First, the number of recursive calls, and second, the time complexity of the additional operations for each of those recursive calls. So what are your thoughts on the recursion strategy? And do you think you can solve the Fibonacci sequence problem using the iteration strategy we covered in the previous video? Let me know. That's been it. Thank you for watching. Hope you found this video useful. Do subscribe to the channel if you haven't already, and I'll see you hopefully in the next video. The Tender. Good day.